In chemistry, we do reactions all the time. It's kind of like our bread and butter activity for finding out how those little atoms and molecules are going to behave. And a chemical equation is that one way that we can use to represent the language of that reaction and communicate what's actually happening during that reaction. You probably know that there are millions of reactions out there, too many to memorize, but you probably also know that we can categorize them into smaller chunks and groups of reactions that behave kind of similarly. Ladies and gentlemen, welcome to AP Chemistry section 4.5. This is all about identifying acid-base oxidation and reduction reactions. In this video, we will look at all three of those, what to look for in terms of identifying one of those reactions, and then we'll look at some problems inspired by AP exam questions. So grab your pencil and let's get started. Let's start, as we often do, by taking a look at the learning objective and the essential knowledge statements. First, the learning objective says identify a reaction as acid-base, oxidation, reduction, or precipitation. Please note that earlier in Unit 4, we spent some time with precipitation reactions and net ionic equations, and later in Unit 4, there's more detailed sections on acid-base and redox. This section, we're simply focusing on identifying which one is which and which one is being communicated to us. So there's a lot of words here, and there's even another page, but I'm going to summarize it all up. If you would like to take a moment and read all of this, you can, and copy it down. I'll wait a second for you to do that. Remember, this is sections on acid-base reactions, which involve the transfer of protons, redox reactions, which are the transfer of electrons and a change in oxidation state, and the third one is precipitation reactions, which involve the formation of solids that come out of aqueous solution, usually. Okay, so that's a lot of words. If you pause the video to copy that down, great. But here's a little chart that I made to really try to simplify things and laser focus on what we really need to focus on. So how to identify the three types of reactions. So we've got precipitation reactions, what to look for. You're looking for solid products forming from aqueous solutions. If you see that, it's a precipitation and you can kind of ignore everything else. Acid-base reactions are all about the exchange of protons, hydrogen ions from one species to another. So you're just looking for hydrogens swapping places. And redox reactions, we'll have to spend the most time on this one, I think, which involves a change in oxidation state from left to right, because we'll have to review those oxidation state rules in case you need them. All right, here is a nice little flow chart sort of organizing our information. So chemical reactions as an umbrella term, precipitation, acid-base, and that sometimes includes gas evolution reactions, like the reaction of an acid with a carbonate, for example, gives you some gas, and oxidation reduction reactions, which involve a change in oxidation state. Combustion reactions, quick note, are a nice little subset of oxidation reduction reactions. Combustions happen when oxygen goes in and oxidizes something else while it gets reduced. And there's a lot of those. Okay, let's start with a quick review of solubility and precipitation. A couple of quick terms that you'll need to sort of be familiar with to communicate. Number one, some things are soluble, meaning they will dissolve in water. And right now we're talking about ionic compounds. Some are soluble, some are not. Some have weak chemical bonds, the ionic bonds, so they dissolve, and some do not. Some are insoluble, meaning they will not dissolve in water. There are some things that are slightly soluble that will dissolve to a small extent in water. We'll get into those when we do equilibrium. Electrolytes are those soluble ionic compounds that you might find in the chem lab or in your Gatorade or things like that. A non-electrolyte doesn't conduct because it's either soluble but not ionic or didn't dissolve at all. Typically, in a precipitation reaction, you'll have one compound that's dissolved, another compound that's dissolved or aqueous. So you look for the aqueuses on the left-hand side, and those two would then somehow get mixed. Right now, there's no magic pairings between those ions, sodium chloride and silver nitrate. When a precipitation reaction happens, at the moment of mixing, all the ions are just mixing. They get in together, they're having a big party, they're mingling and getting to know each other and talking to each other and making small talk for a short time. And after a short time, though, if a precipitation reaction occurs, some of those ions see each other across that crowded beaker, and they feel the magic and they feel the attraction to each other and they group together to form precipitates. This is our solid that is going to come out of solution. So you're looking for solids that weren't there before, but now they are. Now, in our learning statements, they did mention the fact that salts of sodium, potassium, ammonium, nitrate, those are always soluble. And what they're telling us is that we should know that. We should be able to recognize those are soluble. But a lot of these other particular solubility rules, you probably don't need to know. And you can kind of assume that if it's not one of those, that it's probably going to be insoluble or could be insoluble. All right, so let's look at a couple of quick examples. First, here's a complete chemical reaction. All right, it's showing things that lead nitrate, potassium iodide, and then right over here, there's a solid. Keep your eyes open for those solids on the right-hand side because those did not appear over on the left-hand side, and that's typical of a precipitation reaction. Now, it might also be represented as a net ionic equation. We went over this at the beginning of Unit 4, so if you need to head back and check out net ionic equations, you might want to do that. So again, here we have aqueous, aqueous, and then solid. Tip off that it's precipitation reaction. Now, this could be written as a complete ionic equation where anything that's aqueous is separated into its ions, but anything that's together is actually written as together. So so that's your complete ionic equation. It might also be written as a net ionic equation, which are those equations that omit the loser ions, those spectator ions that are there, but they're not doing anything. They're just kind of checking out what's happening, and we get rid of those. So if you see ion, ion, and a solid, that is also a precipitation reaction. Next, let's conquer acid-base reactions. Acid-base reactions are all about the transfer of protons. And for just a quick brief review, there's a couple of different definitions of acids and bases. One put forth by Arrhenius, who said that a substance that just produces hydrogen ions is an acid, and a substance that produces OH ions is a base. The one that's most relevant for us today is the Bronsted-Lowry one. It's the one we use most often, and that is a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. So you're just exchanging protons, like currency between people. It's protons between molecules. And I just want to show you a few so you can see a few what they look like. Here's some acid-base reactions exchanging protons. You have something over here. You got to kind of look left to right to see, oh, there's something here that has a hydrogen, but over here, it doesn't have the hydrogen anymore. And this one had two hydrogens and it picked up a third one. So there's definitely a transfer of protons from one to the other, and that indicates that it's an acid-base reaction. All right. Down here, we have another one where you've got 3 hydrogens and 2 hydrogens. You got to count the hydrogens, essentially. And then we have 4 and 1. So that tells me that one of these hydrogens is making it over to this one, and that is also an acid-base reaction. In this case, the hydrochloric acid is the acid, water is the base. Water is one of those amphoteric substances where if you put it with an acid, it acts like a base, but if you put it with the base, water acts like the acid and gives the hydrogens to the base. So again, looking for that exchange of protons. Sometimes it's written as a net ionic equation, sort of omitting everything else. This is acetic acid with several hydrogens, and over here it's lost one of its hydrogens and that hydrogen has gone off by itself. So sometimes it's represented as the hydrogen just going off into the solution that way. So keep that in mind as well. One of the most typical acid-base reactions that you're going to see is that an acid plus a base makes water and a salt. And I include this because if you see water on the right-hand side of a reaction, that's also, not always, but a good tip that it could be an acid-base reaction, so then you can go back to the left and see if there's anything swapping protons. Finally, let's conquer redox reactions, which can be the trickiest of these three, simply because you're not looking for something as obvious as a hydrogen swapping places or a solid being formed. You kind of have to think about if anything is changing its oxidation state, it's changing its charge. And so you might have to assign those, which is an extra step. So we're going to review our terms, review the rules for assigning them, and try to quickly practice a couple. Again, we'll do this later in Unit 4 as well. So oxidation is the loss of electrons. When something exchanges electrons and gives them away, it's going to become more positive. So you're looking for an increase in positive charge or a decrease in negative charge. Reduction is the gain of electrons. So if I'm gaining electrons, I'm becoming more negative. A redox reaction occurs when one or more electrons is transferred. One loses electrons while another gains them. And so, but again, not as obvious as, say, swapping a hydrogen. Okay, so we know that different elements have different tendencies to gain or lose electrons. Sodium likes to lose electrons and get oxidized. Chlorine likes to gain electrons and get reduced. So assigning oxidation states is kind of one of our skills we have to practice. And of course, I have this chart showing the transition elements again, whose sole goal in life is to make things more complicated for us. Some of those have many different oxidation states, and so we have to decipher and decode which oxidation state it's in and if it's changing at all. The nice thing is that there are other elements, that do make things easier on us. They have their rules. So real quickly, the charge on any uncombined element is 0. You see it by itself, 0. The oxidation state on a monatomic ion is that charge. So like a chloride ion with a -1, that's its oxidation state. Oxygen's going to be -2, except in peroxides when it's -1. That's a kind of a rarer situation, but you can note it. Fluorine is -1, no notes, done. And hydrogen is usually +1, except in hydrides when it's -1. Again, more of a rare situation. But you can use rules like this to decode what something else is that doesn't have a rule, because the sum of the oxidation states for a neutral molecule must be 0. For a polyatomic ion, the sum of the oxidation states must equal the overall charge. So let's take a look at a couple examples, similar to things you might see. And we've got 3 equations here. Identify which element is oxidized and reduced in the following. All right, so I'm going out there and saying, yes, these are redox reactions, but we might have to assign states to see what's changing to what. So I'll do a couple and then maybe have you try one. So in this case, oxygen is -2. Lead doesn't have a rule, but I can tell that it's going to be +2 over here. Same with carbon. Here is +2. And lead by itself is going to be 0. So I can see that lead went from +2 to 0, which is going down, which means lead is getting reduced. Carbon is going from +2 up to +4 because now it gained an oxygen. So another tip-off that a redox reaction is occurring is if there's a swapping of oxygens. It doesn't always happen, but if something's gaining more oxygens, because oxygen is always negative, that means the thing gaining the oxygens is getting more positive. So carbon getting oxidized, lead getting reduced. Okay, so next one, a little more complicated, but we do have some repeats here, which is nice because it can save us some time. All right. All right, so I'm going to start here on the left. Oxygen's -2, hydrogen's +1. They have their rules. Chromium here is +3. Oxygen's -2, and of course the hydrogens are +1, which means carbon doesn't have a rule. But because we have 6 positives and 2 negatives, and 2 carbons have to add up to the remainder of +4, that means the carbon's +2. And over here we have oxygens at -2. In a dichromate ion, chromium doesn't have a rule. But what does chromium have to be so that 2 chromiums plus 7 -2s add up to a -2, which is the overall charge of the ion? And if you correctly guessed +6, then great. And we can see that chromium is going from +6 to +3. That's going down, that's being reduced. And carbon is going from +2 up to +4 again. So that's getting oxidized. Okay, you try. Take a moment and look at this last one, a pretty common redox reaction, and see if you can identify what is being oxidized and what is being reduced. Okay, and if you assigned charges of +7, +4, let's make sure that one's right, +2, and +6. Oxygen stays the same each time. Manganese is going down from 7 to 2. Sulfur is going up from +4 to +6. So if you've got those correct, then great, good job. We are well on our way to mastering this section. And now let's head into our question section. These are inspired by AP exam level questions, and so you might see something similar on your exam. So here's 4 reactions. Which of these represents an acid-base reaction? So we're looking for something that is swapping a proton. Protons transferring from one thing to the next. In A, don't see any protons, don't see any protons. In parts C and D, I do see protons, but the only one where there's swapping from one to the other is that in letter C, the SO3 is actually accepting protons and another oxygen too. And the one of the waters is also accepting a proton to become an H3O+. So that's an acid-base type reaction. All right, same set of equations, but now let's say which one of these reactions shows a precipitation reaction, the formation of a solid. Take a moment, see if you can guess. And if you noticed correctly that yes, there's a solid in A, but there's also a solid in B, and B is coming from aqueous solutions, so B is our choice for a precipitation reaction. Now, you probably know that reactions can be represented in different ways. So here's another one with some Lewis structures. And which type of reaction is represented by the diagram above? Is it precipitation, redox, single replacement, or acid-base? So I'm going to look and say, all right, well, let's see. I've got NH3, water, and now it's NH4. So the NH3 has accepted a proton, and the water has given away a proton. So that means it's an acid-base reaction because a proton is exchanged. There's lots of distractors in there, and that's one of the challenges of an AP level class is that you got to get rid of all the distractors and kind of laser in on what you want to find. Which of these compounds contains an element in the +2 oxidation state? So again, we might have to assign some states, and it's a multiple choice question. You get a minute and a half on average for each of these. So it's helpful to get good at assigning oxidation states. The nice thing is that all of these contain oxygen at -2. So that means the lead is +4, calcium's +2, and there's my answer. Calcium is going to be +2. Nitrogen's going to be +5, copper's going to be +1. And so B is my answer for that one. All right, again, another one with Lewis structures. Which of the following is a correct statement about oxidation and reduction in this reaction? Is it that carbon is oxidized, oxygen is reduced? It is not an oxidation reduction reaction. Carbon is reduced and hydrogen is oxidized. Oxygen is oxidized and hydrogen is reduced. So which one are we talking about here? And I would say that it's going to be letter C because hydrogen's going from 0 in the elemental form to +1. So that's redox. And we need something that gets to be reduced in exchange for that. And carbon is going here from +4 down to -4 because remember hydrogen gets -4. Sorry about that. Because hydrogen gets the +1 charge in something like that. All right. Which of the following, this is a trickier one, contains a species that is both oxidized and reduced? Sometimes the same element can, on one hand, give away some electrons, and the other one picks up some electrons as well. And so we're looking for something in which the same element is oxidized and reduced. So it turns out to be D, and here's why. It's one of those rare peroxide things where oxygen is actually -1 in a peroxide compound. And you had to kind of recognize that, and I'm sorry if that's just a rare situation. But over here, oxygen is 0, but here it's oxygen's -2. So one of the oxygens or pairs of the oxygens goes up, and another one goes down. And so that was a tricky one. All right, you try one. Which of the following types of reactions is represented above? Precipitation, double replacement, oxidation reduction, or acid-base? Take a moment, pause the video, and see if you can get it. And if you correctly noted that iodine is changing charge from 0 to -1, you get an oxidation reduction reaction. And we got two more real quick. Which element in the reaction above is reduced, and what is this element's change in oxidation number? A typical wording for a problem like this. So here's our reaction. And I recognize the fact that there's permanganate and manganese, and I've seen those before in one of our reactions. It goes from +7 to +2, and that is a reduction. And so I'm looking for reducing from manganese, 7 to 2. That is the choice that I would make on that one. So again, a lot of things to kind of wade through. This is part of a typical FRQ where we have element E, don't know what it is, and reacting with a acid to produce EBr4 and some hydrogens, right? The net ionic equation for that reaction. We'll do this real quick. If you need to go back and review net ionic equations, at the beginning of section unit 4, then go for it, is it turns out that the bromine is aqueous both before and after. So the hydrogen, we get rid of that. That's a spectator, and that's going to be a +4, and 2 hydrogens is my net ionic equation. Get rid of the spectators. In the reaction, is H being oxidized or reduced? Justify your answer using oxidation numbers. So hydrogen's going from +1 down to 0. So that is being reduced from +1 to 0. Well, there you have it. Some basics as to what to laser in on to identify acid-base, redox, and precipitation. I hope you found it helpful. You can send me questions in the comments. And in the meantime, happy studying and have a great day.